Assalamu alaikum dear students, welcome to ECA1 class. Today we are going to discuss Kirchhoff current law, which is known as KCL, current divider rule, which is known as CDR, voltage sources in parallel, and open circuits and short circuits. So first we define Kirchhoff current law. Kirchhoff current law states that the algebraic sum of the current entering and leaving a junction or a region of a network is 0. For example, if we have this region, or we say that this is a network or a node, the current entering the node is equal to current leaving the node. We say that this is current entering and this is current leaving. So the algebraic sum of current entering, if we take the positive sign, so we can take the current leaving with the negative sign, is equal to 0. The algebraic sum of the current entering and leaving the node must be equal to 0. Or we can say that the sum of the current entering a junction or region of a network must equal the sum of the current leaving the same junction. You can say that sum of current entering the node is equal to sum of current leaving the node. So we can, if we summarize the Kirchhoff current law, we say that the sum of all the current, either they are leaving the node or entering the node, must be equal to 0. This is basically the Kirchhoff current law. If we apply the Kirchhoff current law to this network, so we consider that, let us take, this is a simple system or junction. The current entering the node is 4 ampere, the current entering this node is 8 ampere, and the current leaving from this node is 2 ampere, and leaving from this node is 10 ampere. So by applying the Kirchhoff current law, the entering the node is basically 8 plus 4, which is equal to 12. 12 ampere current is basically entering the node or the system, and leaving current is, this one is leaving and this one is leaving. 10 plus 2 is equal to 10 ampere. So the current entering the node must be equal to current leaving the node. This will illustrate the Kirchhoff current law. Now let us take an example to understand the Kirchhoff current law. Demonstrate that determine current I1, I3, I4 and I5 for the network given in the figure. So this is the network, and we have to find the value of this I1, I3 and I4 and I5. So from figure we will see that A is a node, B is a node, C is a node and D is a node. So first we apply Kirchhoff current law at node A. You will see that current entering the node is basically 5 ampere, current leaving the node is basically 2 ampere, and current leaving the node is I1. So when we apply Kirchhoff current law to this node, we will see that current entering the node I is equal to current leaving the node, sum of current leaving the node, I2 plus I1. So we have the value of I, which is 5, and the value of I2 is 4. We have to find the value of I1. So I1 is equal to 5 minus 4. So I1 is equal to 1 ampere. So the value of this I1 is basically equal to 1 amperes. Now we have to find the value of I3. So apply KCL to node B. You will see that current entering the node is basically I1 and current leaving the node is I3. So I3 is basically equals to I1 because I1 is entering the node and I3 is leaving the node. So the value of I3 is also equal to 1 ampere. This is also equal to 1 amperes. Now we have to find the value of I4. So apply KCL to node C. You will see that current entering the node is basically I2 and current leaving the node is I4. So we can write that I2 is equal to I4 because this is current entering the node and this is current leaving the node. So the value of I4 is equal to 4 amperes. So the value of I4 is 4 amperes. Now at the last we have to find the value of I5. You will see that we have to find the value of 5. So you can apply KCL at point or node D. So what KCL states that current entering the node, sum of current entering the node is equal to sum of current leaving the node. From figure you will see that I4 and I3 is entering the node and I5 is leaving the node. So we can write that I5 sum of current leaving the node is equal to sum of current entering the node. So substituting the value of I3 which is 1 ampere and I4 which is 4 ampere, so we get the value of I5 which is equal to 5 ampere. So we have find the value of I5 which is 5 amperes. Current divider rule. For two parallel elements of equal value, the current will divide equally. For parallel elements with different values, the smaller the resistance, the greater is the share of the input current. In the parallel circuits, you will see that if we have two parallel circuits and the source current is, for example, 4 ampere, the value of the first resistor is, which is R1, for example, which is 0.1 ohm, and the value of the other resistor is 2 ohm. The current flowing from this resistor nearly equal to 3.9 ampere. This is basically an example to show that the smaller the resistance, the greater is the share of the input current. If you have the smallest value of the resistor, maximum current flow from this resistor in parallel circuits. For a parallel element of different values, the current will split with the ratio equal to the inverse of their resistance values. For a parallel network, the current through the smallest will be very close to the total entering current if the other parallel elements of the configuration are much larger in magnitude. This is basically the extension of this point. Let us consider a parallel circuit in which n number of resistors are connected in parallel. So we have to find the generalized relation for the current divider rule. So you will, as you people know that in the parallel network, the voltage across each resistor must be equal. So we say that V is equal to I1 R1, which is equal to I2 R2, which is equal to I3 R3, and so on. At the end, the value of n resistors is basically IN into Rn, or you can say that Ix into Rx. So It, if we're using the Ohm law, V is equal to IR and I is equal to V by R. The value of V is basically equal to Ix into Rx, and R is basically equal to the total resistance. If we talk about the current, total current, then we write that It is equal to V divided by RT. The value, substituting the value of V, which is equal to Ix Rx, we will get this equation. Now the value of Ix is equal to RT divided by Rx into It. Now you can find the current through any branch using this relation. If we are going to find the current I1 through branch 1, we can write that I1 is equal to RT divided by R1 into IT. So we can define this equation as the current through any branch of a parallel resistive network is equal to the total resistance of the parallel network RT divided by the resistance of that resistor which is of interest and multiplied by the total current IT entering the parallel configuration. So this is basically the generalized relation of current divider rule. You can use this relation to find the current through any branch of the parallel network, parallel resistive network. Voltage sources in parallel. Voltage sources can be placed in parallel only if they have the same voltages. For example, if we have two voltages E1 and E2 which is equal to 12 volt, the equivalent circuit for these two voltage sources that are connected in parallel is equal to E is equal to 12 volt, the total current is added by these two sources. The total current of E1 is basically I1 and the total current of E2, so C2 is basically I2. So when we draw the equivalent circuit for these two parallel voltage sources, we can write I as the total current is equal to the current of source 1 I1 plus the current of source I2, and we have the same potential or same voltage source with 12 volts. So we can only place the voltage source in parallel if they have the same voltages. Open and short circuit. An open circuit can have a potential difference across its terminal, but the current is always 0 ampere. You can see in the figure that, let us suppose this is a system and here it is an open circuit. When there is an open circuit, the current through that open circuit is always equal to 0 and the voltage at this open circuit is maximum. In case of a short circuit can carry a current of level determined by the external circuit, but the potential difference across the terminal is always equal to 0. From this figure, you will see that this is basically a short circuit. Here the voltage is equal to 0 and the maximum current of circuit follow through this short circuit. The current always follow the easiest path. So here is the short circuit and this is the easiest path. So the all current of the network passes through this short circuit. That's all for today's lecture. If you have any suggestions or any questions, you can write in the comment bar. Thank you very much.